If we stop burning fossil fuels today, every car, every furnace, every power station, all at once, how long until the carbon dioxide is gone? The question sounds simple, and there is an assumption hiding inside it. Methane has a lifetime of about 12 years. Carbon dioxide has no single lifetime at all. To see why, we are going to build a planet out of boxes, one box at a time, starting from something you already understand: a bathtub. A box model is the least clever idea in science, and that is exactly its strength. Draw a box around some part of the world. Count what goes in. Count what comes out. Whatever is left over is what is inside. That is the whole equation. And every box in every box model ever built is that one sentence. A box has no interior geography. Everything in it is perfectly mixed, one number for the whole thing, which is what lets a model run 1,000,000 years of planetary chemistry in under a minute. Now give the outflow a single property. It grows in proportion to how full the box is. A fuller bathtub pushes harder on the drain. That one change gives the box a personality and a number, the residence time. Turn it up, and the box takes longer to respond and settles higher. Now drop in a slug of extra carbon. The excess drains away as a clean exponential curve. Hold on to that curve, because the whole argument of this video is that the atmosphere behaves nothing like this box. One box cannot represent a planet, because a planet has places for the carbon to go. So add a second box for the ocean and connect the two. Gas crosses the sea surface whenever the pressure of carbon dioxide is higher on one side than the other, at a rate set by how fast that surface can exchange, about a year. And now everything hangs on one question. When you push carbon into seawater, how hard does it push back? Answer that, and you know how much the ocean will take. There is a fair objection to any model like this, that its numbers were chosen to make the answer come out right. The defense is to make the choosing visible. This model prescribes only quantities that have actually been measured, then derives everything else from a single requirement: that the pre-industrial world sat still. Nobody asked it to produce an export production of 10 gigatons of carbon a year, or a rain ratio of 0.12. Those fall out of the arithmetic, and they happen to match what the ocean is observed to do. Most arguments about models are arguments about judgment. This next part contains none. When carbon dioxide dissolves in seawater, it reacts, and the proportions it settles into are fixed by thermodynamics, measured in laboratories, published with their uncertainties, and remeasured by people who would have been delighted to prove the first group wrong. This panel runs those constants live in your browser. The number to watch is the Ravel factor. Raise the dissolved carbon by 1%, and the pressure of the gas rises by about 10. The sea pushes back 10 times harder than you pushed. Now raise it further, the way 2 centuries of emissions have, and watch that number climb. The buffer weakens as you use it. Now build the ocean up in stages and watch the answer move. Stage 1. The ocean is soda water. Carbon dioxide dissolves into it by Henry's law, and nothing further happens. 2 intuitions compete here. The ocean holds 60 times the carbon the atmosphere does, so surely it swallows almost everything. Or you could run the law and see. Run it, and 76% of the pulse stays in the air forever. Then allow one reaction: the dissolved gas taking water and a carbonate ion to make bicarbonate. And the answer moves by a factor of 4, down to 18%. Stage 2 assumed the whole ocean mixes instantly. It does not. Surface water exchanges with the deep over centuries, and until it does, the deep ocean's enormous capacity is simply unavailable. So the ocean is split into three: surface, thermocline, and deep, with carbon moved between them at prescribed rates. Now, notice what that does to the 100-year answer. It goes up from 18% to 44%. Slowing the ocean down leaves more carbon in the air on human timescales, even though the 1,000-year answer barely shifts. Stage 4. Acidify the deep ocean and it starts dissolving its own floor. The seabed holds a reactive layer of calcium carbonate, the shells of things that died and sank. And when the water above turns corrosive enough, that carbonate goes back into solution, handing back the alkalinity the incoming gas consumed. This is the ocean partially repairing its own buffer. It takes thousands of years, and it can never finish the job because all it does is redistribute carbonate the ocean already had. The pulse stalls at around 8%, and there it would sit forever. Which leaves the slowest process of all: rock. Carbon dioxide dissolved in rainwater attacks silicate minerals on land, and the products wash down to the sea, where they are buried as carbonate. Carbon leaves the surface world altogether. What makes this a thermostat is that weathering runs faster when the planet is warmer, while volcanoes return carbon at a rate that does not care what the climate is doing. Walker, Hayes, and Casting proposed exactly this in 1981 to explain how Earth stayed liquid under a much fainter sun. Left alone, the model settles at 280 parts per million. Nobody put it there. That is simply where the two sides balance. So how strong is that thermostat? Here it is live. Silicate weathering against constant volcanic outgassing. Push the carbon dioxide upward, and the weathering curve climbs above the volcanic line. That gap is the restoring force, and it grows the harder you shove. Drag the gas back below the set point, and the gap reverses. Weathering falls behind the volcanoes, and the air refills. Then comes the number that should stop you. Silicate weathering removes 1/10 of a gigaton of carbon a year. In 2022, we emitted 10, about 100 times faster. Here is every stage on one plot. The fraction of 1,000 gigaton pulse still in the air, from 1 year out to 1,000,000. Time runs on a logarithmic axis, because that is the only way 5 timescales fit on one page. Watch them arrive. Henry's law alone, then carbonate chemistry, then finite ocean mixing, then the seafloor answering, and finally, silicate weathering, the only one of the 5 that ever finishes. There is no single number in this picture. The lifetime of carbon dioxide is a choice about which timescale you care about. One more thing, and it is the part people find hardest to believe. Everything so far has been described in fractions, as though the ocean took a fixed share. It does not. Emit twice as much, and the ocean takes a smaller share of a bigger number. You already know why. Every molecule absorbed eats a carbonate ion and makes the next one harder to absorb. 500 gigatons leaves 43% in the air after a century. 5,000 leaves 70. The buffer is not a constant. It is something we are spending. All of that was an idealized pulse dropped into a pre-industrial ocean. Reality ran a different experiment, and we have the records. So take the actual fossil fuel and cement emissions from 1750 onward, feed them in, and see where the atmosphere ends up. Nothing was fitted to this curve. The parameters were set once and never touched again. The model reaches 415 to 421 parts per million by 2024. The observations say 425. It lands slightly low, for a reason decided in advance. This model has no land biosphere in it at all. But matching carbon dioxide is a weaker test than it looks, because the ocean mixing rates were tuned against the observed impulse response. A model earns trust by predicting something it was never shown. Nuclear testing provides exactly that. Bomb tests through the 1950s and 60s nearly doubled the radiocarbon in the air. A global tracer release nobody would ever have been allowed to run on purpose. From the peak onward, the model decline tracks the observations closely. That is a pass. But the deep ocean comes out about 40 per mil too young. Two mixing timescales cannot stand in for the real ocean's continuum of them. All models are wrong, but some are useful. A model you cannot criticize has stopped being a model and become a sales pitch. So here is the list. Ventilation rates are imposed, not derived. 3 boxes give 2 mixing timescales rather than a spectrum. There is no land biosphere and no permafrost, and both matter most in the first century, which is exactly the period people are asking about. Warming is applied instantly, with no ocean thermal inertia. And one thing this result does not mean: carbon staying up for millennia is not the same claim as temperature climbing for millennia. So how long until it is gone? For a 1,000 gigaton pulse, half of it is gone in 85 years. 3/4 takes 400. 90% takes 3,000. 95% 30,000. And 99% takes 250,000 years. Every step takes 5 to 10 times longer than the step before it, and the pattern never breaks. The curve does not turn and finish. It only gets flatter. That is the assumption hiding in the question. Methane has a lifetime because methane has one destruction process. Carbon dioxide has 5, spread across 5 orders of magnitude in time. And any single number that summarizes them has thrown away the thing you wanted to know.